Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. Today we will discuss inspection of distillation tower internals. Tray efficiency is important for meeting product specifications. Even if all products are on spec, we should still be concerned about maximizing tray fractionation efficiency so as to minimize reflux rates. The more efficient the trays, the less reflux we require to produce an acceptable degree of fractionation. Since the reflux originates in the reboiler, reducing reflux also reduces reboiler energy requirements. As energy is our biggest operating cost, tray efficiency is a major component in minimizing operating costs. The fractionation tray efficiency is largely a function of the vapor-liquid mixing efficiency. The more intimate the contact between the rising vapor and the descending liquid, the better the tray efficiency. The better the tray efficiency, the less fuel we need to run the process. As we have discussed in the previous videos, tray contacting efficiency is mainly a function of two factors: tray deck levelness, weir levelness. Tray deck levelness. For smaller diameter towers, a visual check of tray deck levelness is sufficient. For two-pass trays, a small diameter tower is less than 8 feet. For single-pass trays, a diameter of less than 6 feet is small. For towers of 10 feet or more in diameter, check for out-of-levelness of a tray check using a carpenter's laser level, available in hardware stores for about $40. Purchase a level that has short tripod legs. Use the bubble to level up the legs. Set the level on one end of the tower and check the height of the red beam at the other end and at the center of the tray for out-of-levelness. As it is often dim and dusty in the tower, the trace of the red laser may be clearly visible. Low points in areas of the tray deck that are out of level can now be easily identified. The more level the tray, the better the mixing efficiency between vapor and the liquid. Certainly, if the tray out of levelness is greater than the height of the weir, tray efficiency will be badly degraded. Checking for weir out of levelness is easy. Set the laser level on the edge of the weir. Using the bubble glass level indicator, adjust the laser level to a true horizontal position. The line of red light compared to the top of the weir will indicate how much of the weir is out of level. A weir that is more than 0.5 inch out of level should be readjusted. If it is not, stagnant liquid pools behind the higher section of the weir will result and ruin the tray's efficiency. Loss of downcomer seal due to leaks. The vertical edges to the downcomers are bolted to bars welded to the vessel wall. These are called downcomer bolting bars. Gaskets are often used to tightly seal the edge of the tray downcomer to these bars. If the bolts are loose or if the gaskets are missing, vapor will blow into the downcomer and displace the descending liquid. Downcomer backup and flooding may result. The area underneath the downcomer is called the downpour area. If a tray deck corrodes, it often first holes through in the downpour area. This will cause flooding due to downcomer backup. The bottom edge of the downcomer will be somewhat flexible in larger diameter towers. If the width of the tower is less than 5 feet, then the downcomer bolting bars prevent flexing of the bottom edge of the downcomer. However, if the width of the downcomer is over 5 or 6 feet, then downcomer bracing brackets shown are required. The bottom edge of the downcomer should be immobilized by attachment to the bolting bar or bracing bracket every 4 to 5 feet of downcomer width. Recall that the pressure outside the downcomer is slightly greater than the pressure inside the downcomer. Therefore, a force will push the downcomer toward the vessel wall and reduce the open area of the downcomer. This restriction promotes downcomer backup and flooding. Don't expect to see this deformation of the downcomer during your inspection. Once the vapor flow through the tray stops, the downcomer will spring back to its design position. Effective missing caps. Ignore a few missing valve caps, unless many of the caps are missing in a localized area or the percent of missing caps exceeds 5 to 10%. The caps serve very little function as the open area underneath the cap is about the same as the whole area covered by the cap. The flow of vapor passing through an orifice without its cap may be about 70% greater than the design. Compared to other tray problems, this is not too serious a problem. Repairing loose tray panels. Here's a story that happened in a refinery. The engineer inspected the tower and found two problems. One or two tray panels were dislodged on each tray. The tray panels were encrusted with 0.5 inch of corrosion products. The plant manager was in a terrible rush to bring the tower back online. He instructed the maintenance folks to bolt the trays back up but skipped the lengthy tray cleaning. When the tower was restreamed, the trays flooded at 60% of their pre-turnaround capacity. Fixing the tray panels forced all the vapor to flow through the valve caps. Unfortunately, due to the corrosion deposits on the decks, the tray pressure drop was twice the design DP. This raised the liquid levels in the downcomers and thus the flooding. While identifying loose tray panels is fine, it's best to be careful before changing something that's already working. Improper downcomer clearance. The bottom edge of the downcomer from the tray above should be 0.25 to 0.5 inch below the top edge of the weir of the tray below. This is called a positive downcomer seal. Without a positive downcomer seal, vapor will flow up the downcomer and displace the downflowing liquid. This will cause flooding due to excessive downcomer backup. On the other hand, if the bottom of the downcomer is too close to the tray below, then the head loss under the downcomer will be excessive. Typically, a minimum downcomer clearance is 1.5 to 2 inches. Too small a downcomer clearance will result in restricting the liquid flow from the downcomer. This will also cause excessive downcomer backup and flooding. Check the correct downcomer clearance on the vendor tray drawings prior to the tower inspection. Inlet weirs. Most trays have outlet weirs devoted to maintaining the downcomer seal. But some trays have inlet weirs too, or inlet weirs, but no outlet weirs. A sketch of an inlet weir is shown in this picture. Note the horizontal distance between the downcomer and the inlet weir, dimension X. This distance ought to be equal to or greater than the downcomer clearance, that is, the vertical space between the tray floor and the bottom edge of the downcomer. Unfortunately, a small deformation of the downcomer may push the downcomer quite close to the inlet weir. The resulting reduction in the horizontal clearance between the inlet weir and the downcomer will restrict the liquid flow. This will cause downcomer backup and tray flooding of the trays above. Often, there is no process reason for the use of inlet weirs, especially at higher liquid rates. Then the inlet weirs may be removed. But some tray types, such as Exxon jet tab trays or total trap-out chimney trays with no outlet weir, absolutely require the use of inlet weirs. Seal pans. The downcomer from the bottom tray is submerged in a seal pan shown in this picture to preserve its downcomer seal. Many designers always set the horizontal dimension between the overflow lip of the seal pan dimension Y and the downcomer at 4 inches, so they never have to worry about restricting liquid flow from the bottom tray. This horizontal dimension should be equal to or greater than the vertical clearance between the downcomer and the seal pan floor dimension X, which is typically 2 to 3 inches. If a deformation of the downcomer reduces the horizontal clearance between the seal pan overflow lip and the downcomer, the resulting restriction can cause the bottom tray to flood due to downcomer backup. If the bottom tray floods, flooding will progress up the column. With time, the entire column will flood due to the small restriction in the seal pan. That's why a detailed tray-by-tray inspection is important. Drain holes. All tray sections, draw-off sumps, recessed downcomer inlet sumps, seal pans, chimney trays, and other tower internals must be self-draining. As a column is heated on startup, water can expand to steam with explosive force. Especially for lower pressure and larger diameter towers, tray panels are frequently dislodged due to flashing of trapped water. Experience indicates that drain holes of less than 0.5 inch, drilled in the bottom of a pan, are likely to plug off due to fouling. The better way to place a drain hole is in a vertical wall of a pan, flush with the pan floor, as indicated in picture. Chimney draw-off trays are typically designed to slope toward the draw-off nozzle, thus avoiding a need for drain holes. However, with age, such trays warp because of thermal expansion and pools of water can be trapped. Inspection after water washing will reveal such poorly drained trays and pinpoint the location of required drain holes. But excessive use of drain holes can also be bad. Product losses through the drain holes can be estimated by the following. H equals V squared divided by 2, where H equals liquid level on tray, inches. V equals hole velocity, feet per second. The volumetric rate of flow lost through the drain hole is then the hole area multiplied by the hole velocity. With this equation in hand, your inspection may find drain holes that are best closed. If a drain hole plugs on a bottom tray seal pan, the seal pan will, with time, fill with dirt and corrosion products. This restricts the flow from the downcomer and has caused at least one amine-fueled gas hydrogen sulfide absorber to flood. To avoid this problem, you have to size the drain holes in such seal pans to pass 20% of the liquid flow, or at least use a single 1-inch drain hole. Unless liquid is flushed out of the bottom tray seal pan, the solids washed down the column settle out in the seal pan. Vortex breakers. The idea of the vortex breaker is to prevent swirling liquid from conveying vapor into the draw-off nozzle. Sometimes though, trash lost in the tower during a turnaround gets caught on the vortex breaker. Since the draw nozzle typically is located in a sump below the seal pan, it may be hard to inspect. In some cases, it would be best to just cut off the vortex breaker. This is fine if the nozzle exit velocity is less than 3 or 4 feet per second. The seal pan itself is also hard to inspect, as it is usually hidden inside the draw-off sump. Corrosion deposits may accumulate in the seal pan and cause the trays above to flood. A small mirror is a good tool to observe these hard-to-reach locations. Maintenance folks use this tool all the time. Chimney tray leakage. Establish a water level on chimney trays up to the overflow pipe. Next, crawl under the tray to look for trickles of water. When the tower heats up, such minor leaks are likely to get worse. Also, check the alignment of the chimney hats to make sure they are actually centered over the chimneys. After the water is drained down, look for puddles of water that indicate a need for drain holes. If there is an overflow pipe, check that the overflow pipe will be submerged in its seal pan. Shear clips. If a tower has a history of tray deck damage due to pressure surge or high liquid level, the mechanical integrity of the trays should be upgraded. This is done by the use of shear clips, as shown in this picture. The use of shear clips is not the best way to improve the mechanical integrity of trays, but it is the only effective method to use during a turnaround, when no other plans have been made to mechanically upgrade the tray decks and time is short. Underneath the tray, where the tray panels are bolted together, there is a narrow vertical strip of steel, which is called the integral truss. This truss is not connected to the tray ring. Check this picture. A small steel bar 4 inch by 2 inch by 0.25 inch is welded or bolted to the end of the integral truss. This bar is the shear clip, which is inserted underneath the tray ring. Do not weld the shear clip to the tray ring. When an upward surge of vapor pushes the tray up, the force is transmitted along the length of the integral truss, through the shear clip, to the tray ring, and thus to the vessel wall. Many large diameter towers will already have shear clips. But if your inspection indicates they are not present and tray failure has been a problem, the installation of shear clips is the way to go for 3 reasons. The job can usually be done in 24 hours, while other tower work continues. The shear clips can be cut from an ordinary 0.25-inch carbon steel plate. Experience proves they are effective in resisting moderate pressure surges. Bubble cap trays. About 5% of the trade towers have old-style bubble cap trays. Dirt and coke tends to accumulate under the cap. This cannot be seen unless the cap is removed. Coke underneath the bubble cap will restrict the vapor flow, increase vapor dP, and promote downcomer backup and flooding. It only takes a moment to unscrew a bubble cap using a crescent wrench. The maintenance folks will usually clean the deck, but not remove the caps. Final inspection. In a refinery, maintenance people left a complete scaffold pole, boards, everything in the bottom of a debutanizer tower. Rags, hard hats, plywood, and especially plastic bags left in packed columns should be removed from inside draw sumps and downcomers. It's rough on the knees, but crawl across every tray and look into each downcomer. One lost flashlight in a small downcomer may flood every tray in the tower. A rag caught on a vortex breaker in a jet fuel draw box has caused a complete refinery shutdown. Check the tray clips, tray panels, and downcomer bolting bars. At the least, the nuts and bolts should be finger tight. If you find a single loose nut, insist that every nut on that tray be retightened. Check the tray clips and 10% of the downcomer bolting bar nuts for finger tight. Tower internal manways. Contract maintenance workers often will not replace the tray manways unless the tray manway is adjacent to a tower external manway. They reason that once the tray manways that are visible from the tower manway are closed, there is no way for someone to inspect the other trays. This problem is not just common, it is universal. In a tower in a refinery, it was discovered by inspection team that the 12 trays had their manways stacked in their downcomers. In another refinery crude distillation unit, when the tower was open to implement the design, the tray manways were found lying on the tray decks below the diesel draw tray. The lesson is, inspect each tray and then witness the closure of each tray manway separately. The most important job of the process engineer working in a refinery or chemical plant is to inspect tower internals during a turnaround. The unit engineer and the panel board operator should go through the tower together. Inspecting a 40 tray, 2-pass crude distillation tower properly will take me 3 to 4 hours. It's a dirty, difficult job. It's best not to trust anyone. It's best to see it yourself. Also, crawling through the trays is the only real way to understand how they work and what malfunctions can be expected. It is best to make a list of all nozzle locations relative to the tray number. This will help you to check your location inside the tower. Also, make a list of dimensions from the vendor tray drawings for easy reference in the column. Weir height, downcomer width and clearance, seal and draw-off pans. Most people now use a digital camera to record tray conditions. This is good for record keeping only, not for decision making as to what tray repairs are needed. I suggest you make a copy of the checklist below and refer to it when doing your next tower internal inspection. Tower checklist items. 1. Downcomer seal below weirs. 2. Weirs level. 3. Bottom of downcomers level. 4. Tray clips tight. Trays bolted together tight. 5. Downcomer bolting bars tight. 6. Downcomer bracing brackets installed. 7. No holes in downpour plates, that is, area below downcomers. 8. Tray decks level. 9. All sections self-drainable. 10. Seal pans intact and drainable. 11. Draw-off sumps intact and drainable. 12. Distributors not rigidly supported. 13. Distributor flanges double-bolted tight and gaskets installed. 14. Draw-off nozzles clear. 15. Explosion doors open and close freely. 16. Tray deck panels aligned correctly as per design. 17. Tray deck manways reinstalled. 18. Tower cleared of flashlights, rags, gloves, plastic bags, wrenches, and hard hats. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.